Today we went through the derivation of the Bernoulli equation, and the key result here was after integrating the Euler equation along a streamline, we found that the group P over gamma plus Z plus V squared on 2G is equal to a constant along a streamline. And the assumptions that are built into this is that the integration is along a streamline. Now we're going to see on Friday a relaxation of that. In a particular case where flow is irrotational, we can actually apply the Bernoulli equation everywhere. But for now, our assumption is that this is being applied along the streamline. We'll assume that the flow is steady. We'll assume that flow is inviscid, no frictional forces whatsoever, and that flow is incompressible. And more specifically, actually assume that the density was constant. We went through one example of using the Bernoulli equation today, and I'm just going to set it up again here because I wasn't able to really spend enough time on it. So here we have a fluid that I'm just going to denote in blue that fills our stagnation tube to a particular height. The height of the rise, I'll just call h here. Now the distance below the surface that the tube sits is L. Okay, so we have a fluid within the stagnation tube that is static and rises to some height h. Now the reason it rises is that we have flow approaching the tube at velocity v0. So what we're going to do now is we're going to apply the Bernoulli equation between 2 points. And the first point is upstream, call that point 1. The second point is right on what we call the stagnation point on the front of the tube. That's point 2. So at point 2, V2 is equal to 0. At point 1, V1 is equal to V0. The pressure at point 1 is equal to gamma times L, where L is the distance below the surface. Again, just to note, this is a line that sort of follows right through the center of that tube. So the pressure at point 1 is gamma times L. The pressure at point 2 can be calculated using hydrostatics. And so we go here, say, combine the depth of the tube below the surface plus the height of rise within the tube to say that P2 is equal to gamma times L plus H. So what we're doing is we're using hydrostatics within the tube to define the pressure at the opening of the stagnation tube. Finally, we need to assume that Z1 is equal to Z2, and with that we can then assemble our Bernoulli equation. So P1 over gamma plus Z1 plus V1 squared over 2G is equal to P2 over gamma plus Z2 plus V2 squared over 2G. And now we just make the substitutions for velocity and pressure, elevation, velocity and pressure. And what we arrive at is P1 over gamma is just L. Z1 and Z2 are equal, so I'm going to just get rid of those terms. And V2 is 0. So I have L plus the approach velocity squared over 2G is equal to P2 over gamma is gamma times L plus H. So P2 over gamma is just L plus H. And then that's all that appears on the right-hand side. So the L's cancel, and what we're left with is H is equal to V0 squared over 2G. Or we could rearrange this to say V0 is equal to the square root of 2GH. And that result is actually one that you're going to see a lot when applying the Bernoulli equation. When you have flow, say, exiting a tank where it's at atmospheric pressure, both within the tank and on the outlet velocity is related to the depth of the tank in the same way as this expression, square root of 2GH.